last speaker of today is Victor Gorbenko. He'll talk about quantum groups.
Thank you, Kostya. Thank you for the invitation. It's my first time in IDD, and very nice to visit here. So I will talk about quantum groups as global symmetries. That is the content of the, well, briefly summarized content of these two papers, plus some work in progress. Outline. So we will start with a general discussion of quantum groups in quantum field theory, and I realize that in this audience there are many people who worked a lot on quantum groups and they know what it is, know much better than I do. But still, I will go through some introduction, partial review for the others, but also probably the view on quantum groups that I have may be different from most people in the room have. And then we will discuss specific CFT, which has a quantum group as a symmetry in the way I will define. And then we will talk about related spin chains, and then discuss some interesting future directions. Okay, so why do I and my collaborators, why do we study quantum groups? In fact, for me, the motivation comes from from more general question. Right? So the question is, what is the most general symmetry that is useful for understanding quantum field theory? What is the most general type of symmetry? So the most pedestrian symmetries, they form groups, or if they're continuous, we'll talk about continuous symmetries in this talk, they're Lie algebras. But recently we've observed some generalizations, right? So, okay, not so recently we discovered supersymmetry, so we understood that symmetry does not have to be a group in the literal sense. And then more recently, people discovered what's called non-invertible symmetry. So this is some further deviation from a group-like structure. And then there are generalizations in other directions, like in terms of higher form symmetries. And so we keep discovering new types of symmetries that kind of fall out of the preceding paradigm, and kind of the question, okay, when do we stop? Okay, or what are could there be some symmetries of standard model that we just missed because we're not looking for the right thing? Okay, so that's like the big motivation. So now this is a very hard question. So instead, what we do, we'll take an existing mathematical construction, which is a quantum group, and then we will see what it means for a quantum field theory to have quantum group as, and the emphasis here, as a global internal symmetry. Okay, and I made a little disclaimer. So quantum group is a very sort of rich mathematical subject, and in this talk I will take like an opposite approach. I will try to give an intuitive physical picture. Okay, and then if you want some mathematical details, there are some of them in our papers. Or even better, you can ask my student Sasha Zhabin, who is here, who is much more on top of all the mathematical technicalities. So, and if I start with even further with a sort of a Gedanken experiment. Okay, so imagine an experimentalist who studies some physical system in the lab. Okay. And then she finds that there are many energy states, and with the generalities that go like 2L plus 1, where L is an integer. Okay? And in particular some triplets. Sorry, I forgot to say that first she discovers that there is a U1 global symmetry in this system. Okay? And then on top of it, she discovers that there are some 2L plus 1 degeneracies. And moreover, there are in particular triplets with charges, with U1 charges plus 0 and minus 1. Okay? So then, like a natural conjecture is that actually there is a large non-abelian symmetry that will explain this degeneracies, right? And then this symmetry is SU2. That would be a natural guess. And the prediction of SU2 is that if she measures some 3-point function, then it will be proportional to epsilon IGK, and in particular, 3-point function of 3 nuclear states should vanish. Okay. Then she does the measurement. And she finds that that's not the case. Okay, and in fact, the ratio of the 3-point function of three neutral operators with another 3-point function that actually is also non-zero in SU2 case is some constant. Okay, so that's puzzling. And this is exactly what quantum group symmetry, namely quantum group SU2Q, would predict. And this constant is actually related to this differential parameter Q is whatever, Q squared minus 1 over Q. Okay, so we will focus exactly on this type of quantum group, although I believe on the particular group SQ2, or kind of more precisely Q of SL2, although the belief is that the structure is kind of generic for quantum group-like structure. Okay.
Victor,
Yes.
About the 3-point correlator,
Yes.
what will be measured in that, or what will be the prediction?
Well,
So you expect
the prediction would be in particular that the ratio of these 3-point functions is always equal to this kind of constant, and then so that is exactly the prediction. So if you take operators that are in the same multiplet but have different charges, okay, and then you measure these two 3-point functions. Coordinate dependence can be something, whatever, but the ratio, but it will be the same, the coordinate dependence, okay, and so that is
one here, one there, but with those charges.
Yes, they're at the same point. Sorry, the assumption that they inserted the same. Yes.
Do you know some condensed matter systems also where one could find something like this? So
Well, we will have a spin chain example soon, kind of related to XXD spin chains, as you may guess, and then can experimentalists build exactly that spin chain in the lab? Okay, I don't know.
There would be some. I mean,
it doesn't
could
seem
happen. It's not.
It doesn't seem impossible to me that you can build something like this in the lab. I don't see any reasons why not, but I don't think anyone has built it in the lab. But exactly, maybe if you want, the point of my talk is to understand kind of very physical observables that in principle are even measurable in the lab. Okay, given you kind of have enough experimental precision, as opposed to some kind of abstract structure that underlies something, but that you cannot directly measure. So that is exactly what I want to focus on. Other questions? Okay, sorry. Okay, so this maybe slide again very quickly, because as most of you are familiar, what is UQ of SL2? So it is a continuous deformation of the SL2 or SU2 commutation relations, right? That makes them nonlinear. So there is an operator H, which is this U1 charge, and that's just the usual U1. However, operators E and F, usually raising and lowering operator, they commute on some nonlinear function of H. All right. And then you may say, okay, what is special about this deformation? Why don't I write some other nonlinear function of H here, or something even more complicated? And from a synthesis point of view, important and crucial point is that the representations theory is basically intact. Okay, apart from some special cases, the representations theory is similar to that of SU2, and in particular, there are these 12 plus 1 dimensional representations that have U1 charge that goes from minus L. Okay, then let's think about then what is the crucial difference? And the crucial difference, again, for me, is that the action on the tensor product of representations, referred to as a coproduct, is different. Okay, so for usual global symmetries, if we know how symmetry acts on like some system A and a subsystem B, we know immediately how it acts on the joint subsystem in a quantum mechanical sense, because Hilbert space is the tensor product of the two, right? And the generator is also just tensor product. So for quantum group, this is not the case. So say this U1 part, that is the usual tensor product, but for this E and F operators, there is a kind of non-trivial action on the tensor product of the systems, and moreover, it shows us that ordering of subsystems always has to be important, right? Because you see, it is not symmetric between the first and the second subsystem. So now let me very quickly, again, most people here know, but just to give some perspective, the history of quantum groups, right? So they were discovered in the group of Faddeev and the concept of integrable systems, and then were developed into a mathematical subject, appeared in Chern-Simons theories, and then there was some study related to what I'm going to talk about, but not kind of identical. The approach is that in rational 2D CFTs, quantum group symmetry was discovered and called hidden quantum group symmetry, and I will explain this my understanding of what this hidden means here. Then, on top of it, Bernard and Leclerc, they realized the role of quantum group symmetry in integrable scattering, in particular in the context of Sine-Gordon model, and that eventually led also to identification of quantum group in various worldsheet sigma models. So that is something that definitely people in the room know much better than I do, and something that Fiona tried to explain to me. Okay, put the reference to the previous speaker, but just not to offend anyone. But what I want to emphasize that here also quantum group symmetry referred to as hidden, but I think meaning of this hidden is actually very different between the two. Okay, that at least I try to explain my understanding. And then more recently, quantum groups appeared in a very different subject in so-called double-scaled SYK model and its holographic duals. So we see that this quantum groups appear in some maybe even unexpected places. Nevertheless, not much discussion exists on quantum group as I want to think of it, as a global symmetry of some quantum field theory that it by no means has to be integrable or solvable. Okay. There are some discussions in this papers over here, and most relevant for us in this paper by Pasquier and Saler that we will use later in the talk. Okay, so let's start with the general construction. So how do I implement quantum group as a symmetry of a quantum field theory? Okay, so its action appears very non-local due to having this co-product, which even in the Euclidean sense somehow knows about ordering, even in the Euclidean setting, knows about ordering of subsystems. So usually when I have a symmetry, I can well, visualize or even define it with the help of a topological defect. Okay, so I can so this 1 and 2, there's some objects, say operators, on which the symmetry wants to act, and I act it by drawing this topological line that surrounds the defect. And for normal symmetry, and that is basically a manifestation of this trivial coproduct, I can split this line into two. And basically, if the fact that the quantum group is a symmetry, that is exactly identical to say that this red line is topological, right? I can move it around, and that means that it commutes with the Hamiltonian of the system. Okay, good. So now what we propose to do is to define an action of quantum group symmetry on what's called defect-ending operators. So now instead of having a local operator in my theory, okay, and it could be conformal field theory, it could be quantum field theory. At the moment, it's general. Okay, I take a local operator and I attach to it, to operator itself, a topological line. Okay, so it is a line that I can move around, and the answer doesn't change unless the line crosses some other operator or some singularity. Okay, so now let's be in 2 dimensions. The operators can now be ordered in the following way. So introduce some auxiliary point W, which itself is topological, so I can move it around. But the restriction is that all of my operators have to be connected to this point W. So now you see, even the operators for kind of arbitrary position of operators for 1 and 2, there are 2 ways of connecting topological lines to W, right? One, the O2 line goes above, and in the second case, the O2 line goes below. Okay, and these are topologically distinct configurations, and they define different orderings of my operator.
Could I think as the Wilson line attached, say, to an electron?
There is maybe some analogy, or even more to quark. Okay, yeah. But I do not know if this analogy can be made precise. It's some piece of intuition. Maybe I'll get to it a little bit later. You will see some manifestation of this intuition, but I don't know how to make it precise. Okay. Yes.
Can you clarify how this is an ordering? Because it's not obvious from the figure. I can take O2 and rotate it around.
Yes. So you look, I'm skipping some details, but in fact, when we do it, the prescription, the angles here, we cannot change the angles at which the lines approach this point and approach the operators. So if you keep the angles fixed, then you cannot do it. Basically, if you want, it's like the ordering goes like clockwise around the point W. And so no matter how you rotate, if you're not allowed to change this angle, that's
All right, I get it. So this description is only for 2D.
so far, yes. Yeah.
So like there won't be topological lines in 3D. Is that the
Well, let's not, let's discuss this and then maybe we can at the end of the talk discuss if we can generalize it to high dimension. Okay, that was basically my whatever. Short answer is that I do not know, but I hope that it's possible, but let's not discuss it now. Okay, other questions?
It has to be a line.
Here it has to be a line, yeah, in which,
Because it's 2D. but
in 2D, yeah. Well, you want to go to some high dimensional defects. Let's not directly jump there, okay? Let's try to understand 2D and then maybe we can discuss. Completely mess up the logic of the talk. So let's define now this quantum group algebra generators. So quantum, it's a bit confusing, but you know, like it's called quantum group, but it's more like an algebra, right? So I'm not talking about group-like elements. I'm really talking about algebra elements and their products in this talk. So usual symmetry, as I mentioned, usual symmetry generators are represented by topological lines. So for quantum group, we need some generalization of this object. And what we propose is that, so this black line is, say, the line that represents the F operator. And then there is an additional topological line that is sort of follows, if you want, the current that we integrate over the line. So I should pause here and say that it's not necessary, I think, for the construction to work to have a current. There could be symmetries can be represented just by topological lines that are not integrals of some currents. But for simplicity for us, let's assume that there is also a current. Then this black line represents an integral of a current over this surface. And then the current itself is a defect ending operator. And then the defect should also end at the same point W. And basically, well, this some version of this construction already existed in the Bernard Leclerc paper, but here we're trying to make it very precise. So now there is a non-trivial consistency check that the co-product actually works. So now, if I have my black line, and then this are my operators on which I'm acting, right? And now I'm trying to do the same thing. I'm trying to shrink my black line to write it as a sum of the lines over operator 1 and 2. But then what happens? And here the picture is truncated because it can happen inside a bigger correlation function. Okay, so what you should see is that this dashed line it sort of gets stuck and wraps around this operator 2, and that exactly corresponds to this factor in the non-trivial coproduct. Okay, so coproduct is correctly realized as this set of topological lines. Yes.
Is this like what happens with the knot moves? With the round mice and
yeah, well, and that is probably the reason why quantum groups also appear in Chern-Simons theory, right? And we can imagine that there's probably some duality. Yes, so there should be some relation. I don't understand it in detail, so I cannot. Well, we can happy to discuss, but I cannot give a deep comment on this.
So in this coproduct, there is also the information on whether you're looking at the Cartan or positive moves or negative moves somehow. I mean, from this picture, it's not obvious what should be done.
Well, for me, I think there is a little bit of an kind of ambiguity on actually defining the coproduct, all right? But okay, they're related by some similarity transformation. So for me, I fix the definition of my generators. I fix where is the kind of the definition of my coproduct in this way, and then I don't think there is ambiguity. Maybe I'm missing some technical point, but I think like with this definition that I have, that's more or less a unique picture of some overall similarity transformation. Redefine your operators by some U1 action. Okay, good. So now once I define the symmetry generators, I can now again use the same way as I use the usual symmetry. In particular, how do usual global symmetries manifest themselves? The correlation functions satisfy word identity. So here I can do the same thing, and I can define, derive a word identity. Word identity is some equation that relates correlation functions, right, of operators that live in the same multiplet but have different quantum numbers. And in particular, okay, this is, so usually SU2 word identity would be just, will basically not have these Q factors and will be just telling that the sum will not have these Q and F factors, will be telling us the sum of these correlation functions is 0. Okay, instead here we have some non-trivial linear combination. And basically, after you solve all these word identities, the dependence of correlation functions on the representation index that I call M is fully fixed. In particular, the 3-point function, it has to be proportional to the 3J symbol of a quantum group, right? And that basically explains this relation, this ratio of the 3-point function that our experimentalists discovered from the beginning. Okay, very good. So that was a general picture, and that is, I'm saying, should be true in any quantum group invariant quantum field theory. So now let's have some particular example, and there is example with the call XXEQ CFT. So the reason is the notation comes from the fact that the CFT is actually UV completed by some spin chain that we will discuss later in the talk. So now the torus partition function of this theory has been exactly calculated, and then you can look basically at the spectrum of some low-lying operators as a function of Q. So the Q parameter is related to mu in this way, and then when mu is taken to infinity, Q goes to -1. So Q equal -1 is more or less the same modulus some technicalities at Q equal 1. So this is where we just get SU2 WZW model at level 1, where this quantum group becomes some particular SU2 subgroup of the symmetries of the WZW model. Okay. Good. So I know the spectrum, and now basically the point is that using quantum group symmetry, we were also able to find all the OP coefficients and check these things like word identities. Okay, so for this we use the Coulomb gas formalism. So the claim is that the CFT is closely related to minimal models in a way that I will discuss in a moment. So correlation function is also calculable using the Coulomb gas formalism. So now we want to construct operators and then defect lines of the theory, right? Then we want to find the OP coefficients, as I said, and then check the word identities. So again, for this audience, it's not really necessary just to set up the notation. So in the Coulomb gas formalism, we deal with the free boson theory with the stress tensor modified by this background charge, and this background charge is related to mu. Mu is itself related to Q, right? So then building basic blocks, vertex operators, whose dimension is given by this expression. So now there's a special class of, well, basically two special vertex operators of weight 1, 0 that are called screening charges. And then, as was already understood in the 90s, that this current of the quantum group generators, at least the lowering operator, can be constructed as an integral of the screening charge, right? So this is all the operator of dimension 1, 0. So it is conservable. Good. So now, well, but you will see that there are some kind of, for experts of Coulomb gas formalism, there are actually some important differences with the standard Coulomb gas formalism. I'll try to emphasize. Good. So the theory in particular has a chiral sector of operators. Our theory is not chiral, the full CFC with, but there is a chiral sector. Okay, this is the simplest, so this is what we will discuss in the talk. So then the operators of this chiral sector, they are constructed by starting with a particular set of vertex operators. Okay, so L is the quantum group spin, and the highest weight state is just a vertex operator. Okay. Notice that this is already is a non-local operator because it's not like one holomorphic part. So this has some fractional spin for generic Q. Okay, so this is already a defect ending operator, but it's kind of very simple. And then other operators in the multiplet, they are obtained by acting with the lowering operators. And by doing this, so there's this set of lines, and you see each screening charge can be understood as an integral of some defect ending operator itself. So I keep constructing more and more complicated defect, but at any point it is topological. And actually in this Coulomb gas construction, I calculate how this defect that I then just take and replace with a single, blue line, how it acts on other operators. And then we can check explicitly doing this Coulomb gas calculation that are quite terrible, but you can do them, that the co-product works. Okay, then other properties of the that quantum group imposes on these correlation functions are satisfied. Yes.
Topological line.
Sorry?
Does the topological line preserve the quantum group?
Well, this topological line is needed to define the operator that transforms nicely under the quantum group, well, which is a part of my CFT spectrum. So it's not, you see, quantum group, which is, well, say this black line, right? It's one of the quantum group generators. So, okay, so short answer is that, like, no, quantum group changes the blue line, okay? So operators, different operators in the multiplet, they differ by, well, the operator that sits here can be different, but also the lines are different. So basically what quantum group is doing, it's acting on the operator at the endpoint, but it's also acting on the line, transforming it into a different line. Is that? Sorry? Yeah, transform covariantly, yeah. Yes.
So maybe this is a stupid question, but in the Coulomb gas formalism, you need to balance all the charges, right? And the background contour that we introduced is that counter.
So that is kind of not it's not a stupid question. It's exactly related to the subtlety that I mentioned. So here, this balancing corresponds to having the total U1 charge vanishing for a correlator, right? So just from global U1 symmetry, to have correlator on 0, total U1 charge should vanish. Now, in usual Coulomb gas formalism, you have two screening operators that you can manipulate. And here, to get correct this quantum group structure, you only have one. That is the difference. So it makes your actual correlation function a bit different from what you would get in, say, computing minimal models via the Zenka-Fateev. Okay, let me move on. So to construct generic operators, we need further steps. We need to construct chiral operators with a generic weight, okay? Because so far I only constructed operators with weight 1, 12 plus 1. And then I also need to construct anti-chiral operators with this weight, with weights r, 1, and then I can pair them together. And this is how the spectrum of my CFT looks like. So to do this, to implement the steps 1 and 2, we first imagine sort of a larger theory with as many as 3 quantum groups. Okay, so they're generated by this other. So you see these other screening charges, they're reserved to generate other quantum groups. And then I construct an operator by basically putting all of this together. So this complicated picture corresponds to like all sorts of these lowering operators acting on my operator to first construct members of this theory that has a larger, which has all 3 quantum group symmetries. And then what I do, I implement some sort of projection in this last step. So when I pair my chiral and anti-chiral operators, I take a particular linear combination which leaves only one quantum group, and that is what I call the physical global quantum group. It acts on this indices L and whatever. L is the spin and M is the index on which it acts, while these 2 other quantum groups, we have 3 in total, and 2 of them I pair, and this is sort of answer to Carlos's question. In the terminology of Moore and Rishitikin, in some sense, these 2 other quantum groups, they kind of confined. So I sort of, only consider states that are meson-like with respect to these 2 auxiliary quantum groups. So, but this is okay. So this is what's happening. It's a little bit of a convoluted construction, but the punchline is that there is only one quantum group survived as a global symmetry. And then whatever, using this, we can explicitly calculate. Yes.
And then they mean you will not observe.
Yeah, you do not observe the other. So it becomes like hidden in this language. Okay. So then, okay, then basically this is what I already said, that we compute explicitly correlation functions, and then they are proportional to the quantum group 3J symbols, and that explains this relation that's unknown at the beginning of the
That's that one there.
Yeah, this is just a ratio of some 3J symbol. Good. So now let's discuss very briefly the. Oops, sorry about this. I forgot to erase. Anyway, the quantum groups and minimal models. Okay, so to discuss this quantum group and minimal models, we consider an even more general theory, which actually has 4 quantum groups, right, with all possible screening charges you can have in your Coulomb formalism. And then when you go down to diagonal minimal models, you confine, in a sense, both of them. Well, you pairwise confine all 4 of them. So now in minimal models, all operators appear with, in diagonal minimal models, all operators appear with multiplicity 1. So there is no room to construct non-trivial representation of a non-abelian group. So that's why the quantum group is completely hidden. However, some consequences, they survive. Because we can embed, maybe I say it this way. Because there is this quantum group symmetric theory that I called XXDQ CFT, which has the same central charge as, well, in fact, generalized minimal models. Okay, and the conformal blocks are the same. There's a crossing symmetry. I'm talking about Virasoro conformal blocks. So the crossing symmetry of XXDQ CFT imposes some relation between conformal blocks. That is now related to 6G symbols, right? Because when I pair 3 states under some symmetry, what I get, not 3G symbols, but I get 6G symbols. So there's this relation that was known in the literature between the Virasoro conformal blocks, and in this case it has but kind of a minimal model is sort of miraculous why it appears. It's not a consequence of asymmetry. Well, in our model, this relation is just a simple consequence of global symmetry and crossing, right? Good. And then also I wanted to mention that for a special value of Q, so that the central charge of our theory becomes 1/2, the Ising model, in fact, the fermionic formulation of Ising model, it appears as a subsector of our theory. So our theory has infinite many operators, okay? Solvable, but has infinite many operators. So there's a subsector which becomes an Ising model in this limit, modular, well, maybe some subtleties I'm not going to discuss. So you can see it from the plot. We have 2 operators get dimension 0.1/2. So this is psi and psi bar. And then there is an epsilon. And well, that's what you need for the fermionic formulation of Ising model. And interestingly, the Ising fermions, there are some particular components of the quantum group triplets. So you see, we have this quantum group symmetric theory in which Ising is like a subsector, but if you act, the quantum group does not act within the Ising model, it takes you to some other operator. So this is kind of the structure that we are observing. Okay, this ends the flat space, sorry, the CFT part of the talk, and then I'm going to discuss the spin chains. Are there any further questions?
In this terminology of Moran, of confine, it's like this quantums get gauged somewhat.
Well, it's tempting to discuss it, and it's kind of tempting to. So I have some intuition that should be similar to this sort of JJ bar deformation, so whatever. Many people here work, so you can TT bar deformation for most space time, but for internal symmetry, you can think of some deformations of 2D CFTs. By first introducing some gauge field, then including some action for the gauge field, and then integrating it out. And okay, so say if you start with some SU2 symmetry, right? So this gauging and integrating out will break the symmetry. But maybe in certain cases, instead of breaking it, it could deform it into some quantum group symmetry. So it feels like this, but we were not able to make it precise so far. So that is what I'm saying. So it's tempting to do so, but we were not able to actually make the things work in this language. So, but I'm not saying it's not possible. Maybe we're just not doing exactly the right. Other questions? Okay, good. So now let me discuss spin chain. So why do I want to discuss spin chain? So I presented to you some theory with some non-local operators, and then you would say, okay, maybe I'm just doing something sort of totally random, and my experimentalists will never be able to kind of create any kind of probes that correspond to these operators in the lab, right? Maybe it's again just some abstract sector of the Gilbert space of this spin chain. So I want to argue to the contrary, and that's why we want to go to a spin chain theory and then construct explicitly on the spin chain these operators, and then numerically calculate the correlation function, take continuous limit, and show to you that we reproduce our CFT predictions, right? So this is more or less kind of a standard in at least this type of condensed matter manipulations. Even if you cannot do experiment, if you were able to do like a Monte Carlo simulation that reproduced your continuous prediction, then you sort of it's considered a success. Good. So as most of you know, just taking a usual XXZ spin chain allows us to realize SU2Q algebra on its Hilbert space. However, for usual boundary conditions, the quantum group generators do not commute with the Hamiltonian, right? Instead, there's some part of the bigger structure responsible for integrability of the system. And so in my language, this is not an internal symmetry because it does not commute with Hamiltonian, right? But this can be fixed by adding certain boundary terms. So this is just the XXZ Hamiltonian, and then there are some boundary terms that actually make the quantum group generators explicitly commuting with the Hamiltonian. Yes?
Can you add, instead of this boundary term, can you add other things to make the computation?
Yes, there is at least one other thing you can do. I mean, there are many things you can do, but there's one other thing you can do. You can add some kind of term that looks non-local, but that eventually turns it into a closed spin chain. That's something that we also studied, but I'm not going to discuss it in the talk. So that's why, for example, my CFT, I studied on the plane. Right, and instead this theory, it will flow to a BCFT, right, because I'm on an open thing. But I can also, there's a closed analog, for example. Okay.
You can sort of add a twist to go to like a defect.
More or less, yeah. That's the right way of thinking about it. But again, yeah. Well, let me come back to this. But roughly, yes. So now, we have our spin chain, and then we construct explicitly like a triplet of SU2Q. So you see there is some analogy between so there are three operators, V plus, then we get V0 by acting with a lowering operator on V plus, and then we construct V minus by acting twice. And you see each time I act, the operator becomes more and more complicated. And here, because I have open spin chain, these tails, they instead dressed just to one of the ends. Okay, so I need to choose one of the ends, and then so my point W that I had on the plane now got moved to the boundary. Okay, but you see there's some similarity between constructions. And they say, well, these are terribly non-local operators. Well, they get more and more non-local. So do we even expect to get some nice scaling behavior for correlation functions? And turns out you do. You just do DMRG, take like whatever, 1,000 spin chains, compute 1,000 spins, compute correlation function, and then first, well, even analytically, you can show that these operators exactly satisfy word identities from the lattice. So correlation function of 0, 0 is again related to plus and minus by some 3J symbol, and then you take IJ to infinity, and you get a scaling behavior. And then you get these power laws denoted by the blue circles, and then this is the exact spectrum of our CFT, and you see that there is some value of mu, we get some level crossing, and of course, naturally, on a spin chain, you land on the lightest operator. I mean, there are subleading power laws here, but what you observe is the lightest operator with this quantum group numbers.
What's mu here?
Sorry, mu was related to Q here. Mu is related to C, and mu is also related to Q. Sorry, this is the Q, but C is related to mu. Mu is the usual. Mu is it's like M of minimal model. So yeah, mu is like M of minimal model.
So making mu left, you are getting
mu to infinity. That becomes this term vanishes. So mu goes to infinity. This term will disappear, and then we will just get the usual XXZ. You need to do some similarity transformation. So when you go to infinity, Q goes to -1, so you get a minus here, but then you can transform it into all minus. Okay. Other questions? Okay, so this is very nice. So then I confirm that what we're doing in the continuum is not something ad hoc. Okay, I can just build it on the lattice and take continuum limit, and then I recover something that looks like local operators, as far as scaling is concerned. That is encouraged. It's not obvious by any means. And if you do some slightly different thing, you do not get this generic operators on the lattice that look like this do not scale in the infinite volume limit. Okay, but these guys do. Yes.
It seems like a long range interaction in this 2-point function.
No. This is just a CFT behavior. That's like x minus y to it's a power law behavior. Well, it's long range if that's what you call, yeah, because I have gapless, I flow to a CFT. So I have power law. Okay. But the important point that this delta matches the CFT calculation. Okay. That's as represented by this plot. Good. So let me move to the final point before the conclusions. The point of my talk was that you can think and you can find systems with quantum group just as a global finite dimensional symmetry that roughly imposes the same number of constraints as SU2. Just having, such a finite dimensional symmetry does not have to lead to integrability. Nevertheless, all examples I gave you so far, they were integrable, right? Because I was able to solve them. So you may say, okay, maybe that's actually in some way quantum group always leads to integrability. So I want to disprove this, okay? And to do this, we will consider, again, we were in the same spin chain, but now we add a next to leading interaction of this form. It doesn't have to be particular this form, it's just the simplest one we could find, okay? Where these Ri's are defined below the elements of so-called Hecke algebra, and they all commute with SU2 Q. So basically, whatever you build of these Ri's will preserve the SU2 Q. But in this particular case, it will break integrability. So now, to show explicitly that integrability is broken, okay, because it's, you may say, okay, maybe in some hidden way there's still integrability. So we just do brute force numerical calculation of the spectrum, and then we show that it's chaotic. So maybe I just spend 1 minute, since maybe not everyone here is used to thinking about chaotic systems. So chaotic system you cannot solve, right? So then you approach it a little bit like thermodynamics. In thermodynamics, when you look at 10 to the 23 molecules flying in a jar, you cannot solve for their motion, but you can find some statistical properties of their motion, right? And that's what thermodynamics do. So there's this similar approach to chaotic systems, where you look at some statistical properties, for example, of the spectrum. Okay. So now, actually, for integrable systems, you can also look, even though you know spectrum exactly in some cases, but you can then still look at the statistics of the spectrum. And then they follow so-called, follow Poisson statistics. Well, chaotic Hamiltonians, they have statistics of eigenvalues that actually are, there's a very interesting classification that depends on some, well, basically depends on unitarity, hermeticity, and some time reversal and quality properties. There's like over 30 classes of statistics. But anyway, the main feature of the eigenvalue statistics for chaotic system is that there is eigenvalue repulsion. Well, for integrable system, there is no eigenvalue repulsion because levels can cross and eigenvalues can actually coincide. So it's important, sorry, just on this slide, I forgot that it's to see the statistics, it's important to mod out by all other symmetries, in particular because we have SU2Q symmetry, you're only allowed to look in a sector with given SU2Q quantum numbers. So after we do that, we do our statistics, and then we change our parameter lambda. In particular, what you see on these histograms is the distribution of level spacing. Okay, so the difference of nearest energy levels. So we take, after modding out by the symmetry, we take like L equals 16, we get roughly 1,000 states. And then this, you see if you have, so the blue line corresponds to Poisson distribution, and in particular, it doesn't vanish at zero. So for an integrable symmetry, you're allowed to have some eigenvalues coinciding, so this S takes value zero. While for chaotic system, in the simplest case, you get this sort of what's called Wigner distribution, but all of these distributions, they vanish at zero, okay? Because probability to have coincident eigenvalues is exactly zero. And then you see that when we increase our deformation parameter, we nicely interpolate from Poisson to basically chaotic distribution. That is the proof that the system is actually chaotic. Yes.
Can you find some subsectors of this?
Subsectors.
Yeah.
That are interval.
Well, this shows that that no. Well, to be very precise, what these plots do, they throw away kind of the smallest eigenvalues and the largest eigenvalues. I mean, that's what you always have to do to get the statistics. I mean, it gets polluted by some edge effects. Okay, and in fact, this theory still flows to the same CFT because its deformation we consider is irrelevant. So in some sense, there is a low energy spectrum that still remembers about integrability because it matches to because the deformation is irrelevant in the RG sense. Okay, but modulo this, if you are in the middle of the spectrum, we did not observe any the idea is that okay, look, our numerics are not exactly precise. Maybe we're missing some, but to the extent that we can trust our numerics, we do not see any special sectors or any the idea is that if something like this was happening, you would have seen it as a violation of this of matching to this curve. I by no means I'm an expert on chaotic systems, by the way, so maybe I said something wrong, but that's my understanding. Okay.
It looks like
When lambda is large, it becomes.
Good, yeah, because but that is not surprising because when lambda is large, you actually recover a different integrable spin chain. So that is consistent. Basically when lambda is large, this is your Hamiltonian, and the other one, you can drop the XXZ part, and then somehow in this limit, what is the
At least when Q is equal to 1, then it is integral because it will be XXX in chain, but on side 1, 3, the difference one side is which is
it's two decoupled XXX spin chains. But in Q not equal to 1, it's not clear that it's integrable. But okay, our plots show that it's consistent with also this to be. But yeah, for Q equal to 1, it's known to be integrable, just that thing. Other questions? Okay, so then I have maybe a couple more minutes just to discuss the future directions. So to me, a crucial question for how far this program can go is how non-local the object charge and the quantum group symmetry have to be. And again, generally, even beyond 2 dimensions. So we show that some notion of non-locality should be there, so there should be some topological lines attached to them. However, we see that there is still clustering property, that all correlation functions we considered, they all decay at large separation. So theory is not crazy non-local. But then to address this question, I think it will be good to have 2 things. First, to have some Lagrangian formulation, because what we have like this Coulomb gas formality, but it's not really an honest Lagrangian formulation. And then also consider massive quantum field theories, in particular scattering, because if the theory is massive, then notion of locality is much more sharp. You have exponential decay, particularly sensitivity to boundary conditions is very, very weak. And actually, both of these have been discussed in integrability community, of which, as I say, I know little, but I'm trying to learn. And there is, I think, very interesting directions. However, my understanding is that the role of quantum group is somewhat different. Namely, that the Q now stays for a quantum group charge, whether it's a generic quantum group generator, that it does not commute with an S matrix. Instead, it's some kind of part of this bigger space-time symmetry that generates. You're saying that my interpretation is not correct, but okay. Let me say what I understood, and then maybe you can comment. Okay. So again, that's the impression that I think was at least the case in the Bernard Leclerc paper, from which but okay, maybe what I want to do here was already solved, in which case I will be happy, and then you'll tell me. Okay, good. So what I want to do is actually to modify the S matrices in a way that they strictly commute with the quantum group generators, because then it will be like having really a global symmetry. And I think that there should be some similarity with what was done in the paper by these people, where they realize that actually very well-known S matrices that are some relevant deformation of minimal models that are integrable, they can be modified to respect certain non-invertible symmetries. Okay, and that happens at the cost of modifying crossing. So even like some well-known homologic of S matrices can be at least reinterpreted in a way that they do not satisfy usual crossing relations, but they instead respect certain non-invertible symmetries. Okay, and this I assume by now everyone knows what is a non-invertible symmetry. Okay, there's some discrete symmetry that again does not form a group. And these were identified in minimal model safety. So in particular, because our theory is also related to minimal model safeties, I expect something similar also to happen. So if you insist on constructing an explicit quantum group invariant S matrix, you may need to modify crossing symmetry in some way. And then the question is, okay, well, what it means, and that will address this idea of how much you gave up locality, right? Because crossing is in some sense related to locality. And in fact, I expect more general connections between quantum groups and the discrete non-invertible symmetries. So that is okay, sort of related but independent. The future direction is to make this connection precise. As far as I know, it was not made precise. But again, this is something that maybe in mathematical literature exists in some form, but it is not understood by me. And then, okay, the more ambitious goal is to construct, as someone asked in the beginning, can we construct quantum group invariant quantum field theories in high dimensions? And I'm not aware of any results. I don't see why it would not be possible. So it feels like you need to go to some higher dimensional defects, but again, that's something that we can study. And again, the hint may again come through holography. Because if we have a global symmetry on the world sheet, and I mean the quantum group symmetry is the global symmetry of the world sheet, that basically translates into some isometry of the corresponding manifold in which the sigma model is, which itself translates into a global internal symmetry of let's say CFT if the other part has an ADS factor, or if another part of them. The non-compact part of our spacetime has an ADS factor, right? Then by holography, we will get that this isometry of a compact manifold that we imagine to be a quantum group should become some kind of global symmetry of the high dimensional theory. Okay, so that would be at least a way to make a construction of this kind of unusual symmetry in high dimension. I think would be remarkably interesting. Okay, that's what I wanted to say.
Maybe one comment on scattering.
Yes.
So in general, there are scattering matrices just one symmetry. In this special case of this case where the determinate matrices were studied and the crossing relation was modified based on the non-invertible symmetries. So for those matrices, there was some proposal by Zabological, and then in the literature there were essentially a different proposal, which is the one that realizes non-invertible symmetry. And it was people proposed it in several ways. For instance, Musart and collaborators proposed it based on something that had to do with looking better at the statistics. But there is one proposal, I think, from Luciano, where this is just derived by representation of quantum groups. So the actual is the then to Patrick, Cordova, and Komatsu reinterpret in terms of invertible symmetries, you can see it as emerging as a representation of quantum groups. And this is some work from.
But also the crossing, I mean, generically gets modified, right?
Yes, but yeah, so
Is
I
it-
think it was appreciated already that the crossing was modified.
Uh-huh,
The
uh-huh.
relation to non-invertible symmetries was not appreciated, so we
Uh-huh.
want how to frame this understanding in a more general.
Okay. Okay, it's very good. Yeah, you should
Well, we
you,
can-
you should
I can
explain
give
it to
some
me.
reference.
Very good.
I'm just wondering, you can comment on the relationship or the difference between the framework and CMTFT.
No, that will be hard because I don't understand the CMTFTs. That will be well, but maybe the short. I thought that the CMTFTs that's what appears in this discussion of non-invertible symmetries, right? That's basically the IR remnant of the non-invertible symmetry. And well, okay, maybe I do not know what is the analog for quantum group, and I don't know. I mean, people I don't know, experts to whom I have access also did not know. Maybe someone knows, or maybe that's something we need to figure out. I feel like some generalization should be possible. It should be some more infinite dimensional category, right? But I do not know how to construct it. But I hope that something is possible.
Well, the idea is that like take the solutions of nuclear cell two, do
Yeah.
something to do some kind of transmission. Then like the Wilson lines, like Wilson two lines.
Yeah.
You told them about the defect, but they go up into the third dimension.
Yeah.
But I can still do like all the fusion and braiding, everything.
Yeah, no, I agree at the level of the words. Somehow we were not able to make ends meet, but it doesn't mean. But we kind of didn't try too much, and so I hope it's possible. But if you only can discuss, but we need to write equations. At the level of words, I agree with what you're saying.
So you can.
Well, maybe that's you who we need because I'm not a category. So, yes.
So basically related to the point, your last point there, are there anomalies for these quantum groups?
Again, good question. I do not know. I do not know if I haven't seen any discussion of it. It's in my yeah, because this I'm trying to yeah, okay. It's a global symmetry, right? So it feels like it could be anomalous. Maybe it could be likely it could be anomalous with some usual symmetry because okay, I understand what means. Maybe that's an easy question. So because I know how to gauge the usual symmetry, right? And that should have some universal breaking of this quantum group symmetry. I don't see why it wouldn't be possible, but also, well, you see, you can run into some kind of no-go property, right? Because anomalies are very constrained, like topologically and whatever.
Precisely.
And here there is this locality, there is this line, so there could be some abstraction, but I don't think it's known. No, not to me.
Symmetry, like you can have an army.
Sorry?
The symmetry means you don't have an army.
Yeah. Symmetry means, but the question was, can I have, well, there are like different types of anomalies, right? There could be like real anomalies, or there could be, say, 't Hooft anomalies, right? Maybe simpler, okay, if we stick to real symmetries, we can still ask about 't Hooft anomalies, right? If I introduce a background gauge field for some other discrete, for some other, so you have two global symmetries, quantum group and some other symmetry, and then I introduce a background gauge field for that other symmetry, then that could break in some controlled way quantum group symmetry, right? So I could have this, or okay, I can imagine a system where, yeah, you see the question about usual anomalies. For that, we first need to have some action, right? Because the sort of the question of, I don't know how you call it, not 't Hooft anomalies, but whatever, the anomalies are the real anomalies, right? Where the symmetry is broken, you need to, it's a perturbative statement, right? I mean, you need some semi-classical limit, and here, okay, there are some ideas, again, mostly in the context of integrable sigma models, how to have like an action description, but that's something that again I don't understand yet. So someone should explain to me. Then once we have the action, then we can see if it can be actually anomalous, like, right?
So fantastic question. So the representation theory of Q becomes very special. Q is a unit.
Yes.
And in the that spin chain, this very visible in the spectrum. What about This more general models that we consider?
Yes, this is related very much to this point, but I did not go into these details here. So exactly, so you see here, Q is the root of unity, right? So when I hit minimal models, when central charge hits a minimal model central charge, in particular in this Ising case, Q is the root of unity. And you do get this very complicated representations that are like indecomposable, reducible but not decomposable, and you get some very interesting structure that you cannot. So usually when you have like a CFT with global symmetry, you have Virasora, and it's like tensored with the global symmetry. And here it actually fails. You cannot the symmetry rotates into each other different Virasora representations. But somehow it becomes very complicated. I mean, I can show you how it happens, but we'll have to look in the paper. Also, Sasha can explain it much better. But this is important, and the reason. So the way this happens, these fermions come out of this system is very complicated. In fact, we were not able to prove it. We computed up to we did 8-point function, I think, of these fermions, and it still looks like Ising. But we were not able to show that that all endpoint functions look like Ising. It happens and it's related to this complicated representation. So some cancellations between different terms that, okay. So short answer is that this whatever happens here, and okay, we need like a separate talk to discuss it basically. But I can show you the details.
Any other questions? Not let's take Victor again.